Good morning. Today we're going to get started on Chapter 6, and we're going to begin with Section 1. And what we look at in this chapter, it's actually kind of a challenging chapter because we're going to be looking at different types of lines that we can draw within triangles. And there's going to be a lot of construction problems in this chapter, so I hope you enjoy that part. And a lot of theorems. Sometimes one is hard to distinguish from the other, so we have to take some good notes in this chapter. Okay? So the different types of lines that we're going to be drawing within our triangles are going to vary. We're going to start off, our very first one is going to be perpendicular bisectors. So I'm going to review for everybody what that is. Then we're going to create triangles with perpendicular bisectors, and we'll have a theorem that goes along with it. Right? Then we'll have other types of lines like angle bisectors. You're familiar with that one because I've shown you how to bisect an angle already this year. We're going to have something called an altitude. So that's going to be a new one for us. We haven't talked that one yet. We're going to have something called a median. This is probably my favorite one. There's going to be a really cool part of our construction problems that we do with a median. That's kind of fun. And then I believe, if I remember correctly, the last one that we're going to be drawing is called a mid-segment. All right, so those are the different types of lines we're going to draw within triangles, and we'll show you what's true about these, and then doing construction problems with each one. Okay, so we'll get started with the very first one here. So in section 6.1, the first type we're going to look at is what's called a perpendicular bisector, and our definition is pretty simple. This is just going to be a line which is perpendicular to a segment and which bisects the segment. And remember, bisect means cut into two equal parts. All right? So what we're going to start with is a segment. So we'll just have a segment drawn somewhere. And remember, a segment is a portion of a line with two endpoints. So maybe we'll call the endpoint something like A and B. And now if we draw a perpendicular bisector to that segment, the line that we draw is going to do two things. It's going to be both perpendicular to the segment that we started with. So it's going to be perpendicular to the segment we started with, and it's going to bisect, cut the segment into two equal parts. So if we call this point in the center right here C, then the result is going to be that the length of AC and the length of BC are going to be equal. Okay, and again, just to repeat, all of the angles at C, all four of the angles would be 90 degrees because it's also perpendicular. Okay, so that's what a perpendicular bisector is. All right, and now here's the theorem that goes along with that. And like always, please feel free to pause the video if you need to make sure you get something into your notebook. Okay, but here's the perpendicular bisector theorem, and it just simply goes like this. A point lies on on the perpendicular bisector if and only if the point is equidistant So equal distances. Equidistant from the endpoints of the segment. So a point lies on the perpendicular bisector if and only if the point is equidistant from the endpoints of a segment. Okay? So please remember the if and only if problems. The if and only if problems work in both directions. So I'm going to draw you two pictures. All right. So it's just going to take me a minute. So we're going to have a segment. We're going to have a line. Okay, so here's my line. I'll call it L. Here's my segment, AB. And the theorem says a point lies on the perpendicular bisector if and only if the point is equidistant from the endpoints of the segment. So one direction would be any point on the perpendicular bisector. I could choose this one, or this one, or this one, or this one, or any of these down here. A point lies on the perpendicular bisector if it's equidistant from the endpoint. So if we pick a point on the perpendicular bisector, so if we know that this is the perpendicular bisector, then the distance to the endpoints are going to be equal. So these distances would be the same. Or these distances would be the same. So if we have a perpendicular bisector, then that point is going to be equidistant from the endpoints of the segment. Okay? So if I scooch this up a little bit, I'll write that out to make sure everyone's okay. So if L is the perpendicular bisector of AB, then, and I need another point up here, either C or D, then the distance from A to C and the distance from B to C are going to be equal, or any other point, the distance from A to D would be equal to the same as the distance from B to D. So that's one direction. If we know where you have a perpendicular bisector, then any point on the perpendicular bisector will be equidistant from the endpoints. And then the other direction, again, let me get you started with a picture. Oh boy, that's lousy. Let me try that again. It turned out poorly. All right, so a second picture. So I have a segment, I have a line, but this time I'm not starting with, I know I have a perpendicular bisector. This time instead, I'm going to start with a point somewhere on the line, let's call it C. And if the distance from A to C and the distance from B to C are equal, so if the distance from A to C and the distance from B to C are equal, then what we know is that L is a perpendicular bisector of AB. And I'll write the rest of that out. Then L is a perpendicular bisector of segment AB. So it's one of those theorems that works in both directions. It works in both directions. Okay, so feel free to pause the video to make sure you get the theorem down. And I'm not sure if you want the two pictures or not, but like always, that's up to you guys. Okay, then I'm going to go through some numerical problems using that theorem. So we'll start with real easy ones, right? Real easy ones. So I'm going to start you off with a segment. Then I'm going to draw a line for you. So let me get this set up. So here's my segment. Here's a line that I'm drawing. And I'm going to show you that it is the perpendicular bisector of the segment. Okay? So what I'm telling you is that L is the perpendicular bisector. Now, if we were to pick a point on the line somewhere, like this point right here at C, and I told you this distance from A to C was 27, then do you know for sure what the distance is from B to C? And what the theorem says is, if we have a perpendicular bisector, then any point is going to be equidistant from the endpoints. So therefore, if AC is 27, then BC would also be 27. So if you know you have a perpendicular bisector, then pick any point on the line. It's equidistant from the endpoints. Okay? So there's one example. Again, real easy, I know that. But still, trying to get you that idea, okay? Here's another one that I think you'll find pretty easy, but I'll jog through it anyway. So here we have a segment. I'm going to draw a line. So here's my segment. Continue to just call it AB just to be consistent. And once again, we're going to pick a point. So I'm going to choose this this point right here. And again, just be boring and call that C. But this time I'm not going to tell you that we have a perpendicular bisector. Instead, what I'm going to do is I'm going to show you that the length of AC is 13 and the length of BC is 13. Right? Next, I'm going to tell you the length from A to D is 5. And then I'm going to ask you two questions. What's the length from B to D? And what's the length from C to D? Right? So can we answer those two questions? Okay? Well, the idea is we're using the theorem in the other direction. If the distances from a point to the endpoints of a segment are equal, if the distances are equal, please notice A to C is 13, B to C is 13. If the distances are equal, then the line must be the perpendicular bisector of the segment. So we're using the theorem in the other direction. Okay? And so therefore, if it's a bisector and length AD is 5, the length from B to D must be 5. And I'm going to put it in a different color just so you kind of catch that. It wasn't there to start with. So from B to D must be 5 because it has to be a bisector. Okay? Then, can we get the distance from C to D? And again, I'm going to highlight it in blue or something here just so it stands out. Can we get that length? Right? Well, at first you might think, well, I'm not sure how to get there. But going back to something we've done before, something called Pythagorean theorem. And I don't mean we've done this in our geometry class, but we did it in algebra after I came back last spring. We know that if we have a right triangle, and this side is 13, and this side is 5, anytime you know 2 out of the 3 sides, you can find your missing side with Pythagorean theorem. You might remember it as a squared plus b squared is equal to c squared. But the key is that the c, the number by itself, has to be what's called the hypotenuse. And in our case, that's going to be the 13. So what we'd have then is 5 squared plus question mark squared is equal to 13 squared. And of course, you guys are good enough to solve this. 5 times 5, 13 times 13. Move the 25 to the other side by subtraction. And get rid of the power of 2 by taking the square root of both sides. So the missing side is 12 long. So CD would have a length of 12. All right, look okay to everybody? So again, we can use the theorem in both directions, starting with a perpendicular bisector and then using the fact that any point is going to be equidistant from the endpoints, or backwards, start with the distances from the endpoints being equal, and then that forces the line to be a perpendicular bisector. Okay? Alrighty. And then we can just make the problems a little bit trickier. So let me give you another example. So once again, I'm going to start with a segment. I'm going to choose to go this way. I'm going to have my line going this way. And let me emphasize, again, I'll just be boring and keep the segment as A, B, just so you don't get mixed up on that. And once again, I'm going to show you, I'm going to use the theorem in the one direction that says the line is the perpendicular bisector of the segment. So I'm starting you off in that direction. But this time I'm not going to pick one point, I'm going to pick two. I'm going to pick one point right here, call it C, and another point over here, call it D, and then I'm going to connect. So I'm going to connect the endpoints of the segment to C, the endpoints of the segment to D. And what our theorem says is, when you pick any point on a perpendicular bisector, those two distances are going to be the same. And of course, the same is true at D. Those two distances are going to be the same. So if I were to tell you that this side is 6x plus 11, this side is 11x minus 9, this side is y plus 11, and this side is 3y minus 15, would you guys be able to find the values for x and y? All right? The idea is relatively easy. As long as you remember the theorem, any point on a perpendicular bisector is going to be equidistant from the endpoint, so therefore, this length from C to A and this length from C to B are going to be equal, which allows you to create the equation 6x plus 11 is equal to 11x minus 9. And for you guys, that's a very easy equation to solve. Variables to one side, numbers to the other side, and get rid of times 5 by dividing. And so x is going to be equal to 20 divided by 5, which is 4. And then similarly, picking point D, being on the perpendicular bisector, means the distance from D to A and the distance from D to B have to be equal. Again, allowing you to create a really easy equation. 3y minus 15 is equal to y plus 11. And again, you guys can solve this easily. Variables to one side, numbers to the other, get rid of the times 2 by division, and so y would be equal to 13. All right, so for the most part, the equations become fairly easy. They become fairly easy. All right, and then we're going to finish this first half of section 1 with a proof. So we're going to use our theorem to help us do a proof. So let me get you a picture set up and then probably pause the video so that you can copy the picture well. All right, and then I need a line coming up. Oop, I hit the wrong button, darn it. Let's see, sorry about that, guys. Hit the wrong button. There we go, now we should be okay. And finally, there, and there. Okay, so there's my picture. I've got some letters that we'll use for the vertices. So N, M, P, O, and this point we're going to call R. All right, so there's my picture. Now I'm going to give you some information like we usually do. And in this case, what I'm going to tell you is that NP is the perpendicular bisector of MO. And what I'm going to ask you to help me prove, is that two angles, and I'm going to show you the angles in red here. So this angle, number 1, and this angle, number 2, are equal to each other. Right? So how can we get that job done? So again, just to repeat, feel free to pause the video to get a decent picture, to get the given, and to get the prove down on your notebook. Okay, so once you're ready to go then, like always, we begin with given information. So NP is the perpendicular bisector of MO. So that's given to us. Okay? Now, what that helps us with is now we have the theorem. Because we have a perpendicular bisector, because I have this perpendicular bisector, I can now apply the theorem, which says if you pick any point on the perpendicular bisector, it's going to be equidistant from the endpoints of the segment. So what I want you to think of is I want you to think of the original segment as being the bottom of the triangle. And I'm going to put it in a different color just so it's highlighted. So I'm going to ask you to think of the bottom of the triangle, M to O, as being the original segment, and then NP is the perpendicular bisector. Okay? So our theorem says you pick any point on the line and it's going to be equidistant from the endpoints. So as an example, if I ask you to pick point R, so you pick point R, that then has to be equidistant from the endpoints of the segment. So what we could say then is the distance from M to R and the distance from O to R are going to be equal using the perpendicular bisector theorem. Right? And I know I haven't talked about what triangles I'm using yet, but just give me a minute, please. Give me a minute. Then if you picked point N, our theorem once again says pick any point on the perpendicular bisector. It's going to be equidistant from the endpoints of the segment. So what that tells you then is the distance from M to N and the distance from O to N are going to be equal using the exact same theorem. Okay? And now if I highlight, after doing those two things using our theorem, now highlight for you guys the triangles I was looking at. I was considering this triangle that goes from M to N to R, and the triangle that goes from O to N to R. Those are the two I happen to look at. And you might notice that if I ask you to focus on the blue and green triangles, right now what we would have is two sides. Right? M to R, O to R. M to N, O to N. Those would be two sides of those triangles. So to prove the triangles are congruent, we'd either need an angle or another side. And it's very easy to get the other side because there's a shared side between the triangles. So we could say then that NR in the blue equals NR in the green. And of course, anything is equal to itself using the reflexive property. And that gives us another side. So in the margin, SSS, hey, those two triangles must be congruent. So the blue one, MNR, and the green one, ONR, have to be congruent. SSS, three sides of one equal three sides of another. And once you've proven triangles are congruent, then any corresponding parts are also equal. So we can finish by then saying angle 1 is equal to angle 2 using CP/CTC. Corresponding parts of congruent triangles are congruent. Okay? So that takes care of the first type of line that we're going to draw within triangles. That's the first half of section 6.1. Because of the length of the video, I thought this would be a good time to pause, turn this one off, and then have a second video that takes care of the second half of section 6.1 and the second type of, the second type of line that we're going to be drawing eventually within triangles. Okay? So hope this finds you guys doing well. We're about halfway through the class period, give or take. So please then shut the video off and go ahead and get started on the assignment. Tomorrow I'll send you the video for the second half of this section. And then Friday I'm going to just give you guys kind of a day off and let you watch a YouTube video or two just for fun. Okay? Alrighty. So hope this finds you guys doing well and hope to see you real soon. See ya.